I don't think air columns are as confusing as that note made them sound. What's key about them is only a particular wavelength will fit into the air column and make it resonate so nice and loud. So that's the connection to resonance. It only happens at particular wavelengths. Resonance is a little bit complicated. Some things can resonate at different frequencies. That kind of connects to it too. So in this particular one, I'm telling you that it's the third resonance. That tells you kind of about the shape of the standing wave that's fitting into the 90 centimeters. The question says it's open at both ends. That's kind of key too. Sound is a longitudinal wave, but for the purposes of air columns, we imagine sound as a transverse wave. Then we can connect it back to our standing waves on strings that we talked about. The rule is we're going to picture it as a transverse wave. There has to be an antinode at the open end. So this particular one, since it's open at both ends, is going to start and end with an antinode. If it was the first resonance, this is what the standing wave would look like. One antinode to the very next. If it was a second resonance, I just add on another one of these. They're kind of a sideways hourglass shape. That would be the second resonance. The third resonance would be one more of those hourglass shapes. That's what the third resonance looks like. If I trace it, a full wave goes to there, and then I've got another half. So really what's going on is I've got 1.5 lambdas fitting into the length of the pipe, or the length of the air column. This one says that the air column is 90 centimeters. I need to put that in meters. Do a little division. I've now figured out that the wavelength is 60 centimeters, or 0.6 meters. So from the wording of it, the name of it, third resonance, I drew the shape and then applied a bit of logic with the length of it to get the wavelength. That was labeled as part 1. For part 2, moving forward, whenever we know the temperature, that really tells us the speed of sound. The speed of sound goes 332 plus it increases by this weird 0.5 number for every degree Celsius. So this means the speed of sound is 332 plus the 0.5 number multiplied by the temperature I made up, which was 15. You can double check my math. I get pretty much 341. If we carry the decimals, it's 340.85. That tells me the speed of sound at 15. I know the wavelength from part 1. The connecting equation is I know that V is always equal to F lambda. I want to know F. We always talk about sounds in terms of their frequency. That's going to be V over lambda. In this case, 340.85 meters per second divided by 0.6 meters. We end up with a number in per seconds, which we're going to call hertz. And within rounding, I'm getting 568.